I've been working on for some years now, just to help the robotics community here in Nigeria, Africa, and beyond. So I'll be presenting now. Please, if you can still see me, you can see the presentation. Please do let me know. And if you can't see it also, please can give the feedback. Thank you. So about me. So like I said earlier, I'm a robotics and a software engineer. Actually, I'm passionate about bridging the gap between theory and practical application in robotics, and I specialize majorly in mobile robotics, hardware, simulation, control, and navigation. So those are my general specialty. Now, I started in 𝗟𝗏𝗃𝗄𝗿. I'm currently running an organization, a company called 𝗟𝗏𝗃𝗄𝗿, and I started it to empower individuals and organizations to be able to build advanced mobile robotics systems, leveraging open source framework like ROS2, Arduino, and the likes, just to build advanced robotics system. And I have a mission to ensure the growth and longevity of open source robotics, both in Nigeria and Africa and beyond. So the purpose of the talk actually is just to, like I said earlier, to introduce robot and hardware solutions that I'm currently developing at 𝗟𝗏𝗃𝗄𝗿 that will help accelerate advanced mobile robot learning and development in Nigeria, in Africa, and beyond. And I think this will be beneficial to the ROS community as a whole, especially ROS Niger. So, and the robot I'll be talking about first is the mobile bot, and the two hardwares I'll be talking about is the EPMC module and the EIMU module. So first and foremost, I'll be talking about the significance of the talk. So what's the importance of what I'm about to say, or this particular short talk? We all agree with me that as ROS developers or robotics engineers, for those that are into it, simulation is very good. A lot of us maybe might have get hands-on the basics and run some simulation, but simulation is good. But the thing is that in a place like Nigeria, like this, you agree with me that we like to build things. We like hands-on things we can do with our hands. That's the truth here. And for students, you agree with me. For those that are in school, maybe your supervisor asks you to build a project, you most likely not be presenting simulation to your supervisor or the panel. You most likely be presenting something real, something you worked on. So we like building things here. And also, as robotics engineer, is an added advantage if you have the ability to work with hardware and use real sensors or work with real robots. Building advanced mobile robotics system is a core added advantage for you as a robotics engineer in this time and in this age. So, and we can also see that when you are developing advanced robotics system, see that it requires precision, controls, reliable sensor, hardware integration, and things like that. But you also agree with me that a lot of the robots that we have, or most, suffer from one key issue: poor base control, and also things like sensor filtering, being able to implement advanced algorithm on real robots like SLAM, localization, and navigation. I've had people reach out to me. They want to do maybe their final year project or projects like that. They're asked to implement SLAM, navigation, sensor fusion, but it all boils down to some of all these things. We don't have the hardware or the capacity for things like that here. And most times, if I direct them online, okay, try and get this hardware, get this robot, money issues, or even maybe to get it and to work with them, fear and things like that. A lot of things affect it, and most people just stop the work they are doing, or just end up building something simple so that maybe they can grab it or just move on with their life. But I'm hoping that with this we can develop ourselves as robotics engineer here in Nigeria. And like I said, lastly, because there's a shortage of accessible robotic platforms for advanced robotics learning with ROS. So that this is why I believe the solutions and the things I'm about to present to the ROS community will be beneficial to the ROS community. So I'll start with the robot. Yeah. So this is MobileBot. MobileBot, I did a post on it on LinkedIn recently, and I called it the Nigerian 𝗏𝗏bot. We're all used to 𝗏𝗏bot, and basically it's just a compact open source mobile robot, and it was designed for students, maker, engineers, and those that are interested in exploring robotics, advanced robotics with ROS2, and it has both simulation and hardware. It works with NAV2, SLAM toolbox, robot localization, sensor fusion with EKF, ROS2 control, and even the popular OpenCV to aid hands-on learning in concepts like control, sensor fusion, state estimation, application and perception, even artificial intelligence. So that's why I actually made it. And the core features is that it uses a Raspberry Pi RP LiDAR, and then it uses two particular modules, which I'll be talking on later in this presentation, the ePMC and the EIMA module for its base control and sensor fusion. It also has the USB camera, and it has a gazebo simulation, just like the 𝗏𝗏bot. So it's something you can get started with. It's easy to work with, and it was designed for this. Number one, to be easy to work with and to build. So if it's something you want to also build on your own from scratch, it's something you can do that, or it's something you want to get and work with it directly. It's built, it's designed that way. And in this short, these two videos or these two GIFs, notice a test. I'm just doing a test on it. So this is the test using both navigation and the camera streaming. This means you can work, designed so that you can work with it from your laptop connected to the robot and start testing algorithm, viewing it, RVs, viewing images, writing notes that can communicate, with the actual robot, and seeing your algorithms come to life. So that's the whole point. And just a final note that the MobileBot is still in its final development phase, but it's actually open to contributions presently. So there's a link at the end of the slide for the documentation. You can check it out, try out the simulation, and reach out for those that are interested in contributing or getting one. So and that's that on the MobileBot. So I'm talking about two hardwares. One is the ePMC module, and the meaning of the ePMC just simply means Easy PID Motor Controller Module. And basically, what's the ePMC module? It's just like an easy to use open source motor controller. And what it basically does is to provide precise speed control for any geared DC motor that use quadrature encoder. If you have ever used a servo motor before, maybe computing starting, you notice you can send angular commands like 0 degree, 90 degree, things like that, and you see the servo motor maybe moving to that particular angle. That's exactly how the ePMC module works. So you send actually angular velocity command in radians per second, and you can see your wheel moving at that particular velocity, and you can get feedback from it. And the way it was designed such that it looks like the 𝗟𝗏𝗏 driver module. Since I know that in a place like this, we are used to 𝗟𝗏𝗏 driver module. I have a sample here. This was just the final design I worked on recently. So, and it has precise control and capabilities, and you can use it with ROS2, your PC or Raspberry Pi, and this is how the motors are connected. The ports are available for connection. So more on the ePMC module, and is that there are two key features that I think will be relevant to the ROS community. First is the GUI application. Once you get it, you can easily connect it to the GUI application and to set up things like your encoder, force per revolution parameters and your PID parameters. Then it also has a ROS2 hardware interface where you can easily interface it, with ROS2 to set up your base control, and you can see the different images here to show you that. And if you look at the hardware interface parameters, they are not scary, they are just things that you just need your port and then show the module where you connected your left switch and your right switch, and you are good to go. And that is designed to be easy to work with. An example of DC motor that is quadrature encoder, I believe we are used to motors like this, and that's the whole point of creating this kind of module. So motors that uses quadrature encoder, so these are their examples. Most of us are quite used to this. Yeah. So and the other hardware that I'm talking about is the easy IMU module. That is the EIMU module. So it's also similar to the EPMC module. It's just an open source advanced IMU system. I designed this for the MPU 9250 IMU, and what it does is provide easy to use filtered orientation reading using the magic filter, and it can be configured in any reference frame. But these are the basic issue we have when we are working with some of all these hardware that we use for our robotics system. For example, as ROS developers now, you'll be working more with the ENU reference frame, that is the East North Up reference frame. So you can configure it to any reference frame, and you can easily use it, integrate it into your robotic system. For those that are into drone development, you use the NED reference frame, which is also a reference frame that this IMU can be configured into. And more on it, like I said, similar to the EPMC mode, it also has a GUI application to ease up the calibration and the setup of the IMU. You can set up the covariance, a lot of things, the variant, the sensor variant, and things like that. A lot of things you can just set it up at click of buttons. And it also has a ROS2 package for easy integration with ROS2. And these are the pictures of the hardware. Yes. So the general application of the EPMC module. Remember, when I was speaking about the significance of the talk, was because I noticed that generally our robots here, we have poor base control. Because of that, our robots cannot do things like state estimation, cannot have odometry readings, filtered odometry, and things like that. So, and this is one of the key uses that can help you build your robot, setting up that base odometry with sensor fusion. So these are things you can use with this, can set up with this hardware and build a mobile robot with full base control. And that's one of the key power of the mobile bot, these two hardwares. And other applications like precise motor control, speed control, or autonomous mobile robot, drone development, the IME for drone development, heading reference system. Those are into ROS or ROS2, or even other framework like Arduino, Python, C++, but because the talk is about focusing on ROS, so that's why I'm focusing on ROS2. So in conclusion, you can see that I believe these hardware like the mobile bot and the EPMC and the EIME mode, I believe it will make advanced robotics learning and development more accessible to ROS developers, and see that they address the key challenges we are facing here, generally in Nigeria and even generally in most developing countries, that building mobile robotic system and empowering those developers so they can focus more on the innovation. We want to build things, but to start building these things from scratch, the right hardware, until there is a problem for us here. So you can focus more on the innovation. I think Mr. Sikiru said a lot of things about this particular point in one of his posts on LinkedIn. So then also, since they are open source, these are things you can explore, experiment, you can get them and explore them, experiment. You can also contribute to the development. And just the final note that they're actually in their final stages of development. So the documentation is there. You can check it out if you are interested in using and testing them and contributing to them. I would love to hear from you. So this is the link to the documentation. Thank you. Feel free to reach out via email or LinkedIn personally. And thank you for listening.
Right. Thank you, Samuel. Thank you so much. Do you have any other things to still display?
No, I think that's all.
All right. So if you have any question for Mr. Samuel, you can ask your question, please. If you have a question. So if you have a question, please reach out.
I think someone has a question here.
That's Mr. Sheriff.
Good morning, Mr. Samuel.
Good morning.
Thank you for the presentation. Although I joined a bit late, I just want to ask, how much is it going to cost to procure the Mobot? How much does it cost to procure it?
Okay, so for the mobile bot, presently, like I said, it's in final stage of development. So it's not actually available yet for maybe purchase or pre-orders or things like that. So it's maybe before Easter, I think everything should be done. This was just the initial test that I shared on LinkedIn to make people aware that something like this is going on. But feel free to email me so I can reach out to you as soon as it's available. Yeah, thank you.
Okay, thank you.
All right. So somebody in the physical session here, we asked a question, and then after that, 𝗟𝗂𝗃 Samuel can go ahead. But let somebody here ask a question.
Okay.
Yeah. Thank you for the session. It's really insightful. So my question is about the EIMU for drone development. So can you just tell, like, what does it do, like, exactly? Like, how does it stabilize the drone? Maybe you can explain, like, application of the control system, because I think I'm more interested in that.
Sorry, I didn't hear you very well. You're talking about the EIMU.
All right. So my question is,
okay.
Let me take it again. Sorry. But my question is about the EIM. You said it is for drone development for ROS. So I think I'm more interested in that. So can you just maybe talk briefly about it in terms of drone development, like in terms of stability and the rest? So how can it really help drone development?
Okay, so in terms of drone development, like I said, it can help in because actually what it does is that you get filtered orientation reading using magic filter, like your raw picture, your reference frame for drone development. I know you use the north east down reference frame. So you easily those orientation reading, you get them filtered already. So you can easily use it in your group for stability and drone application. Although, like I told you, my test experience now is I work with mobile robots, so I've used it for mobile robots. Like I said, it's open for you can get it, test it, and try it out. We'd love to hear your thoughts. If you are using it for drone development, to try it out and see how it actually works. But because of the filtered orientation reading, it will help with stability of drones and things like that. So you can try it out, try and integrate it and see how it works. So yeah, thank you.
All right. So I think Samuel can go ahead with your question.
All right. Yeah, good afternoon, everyone. So I was actually meant to join you guys, but due to long distance and traffic, I couldn't get to Milan on time. But I have just two questions. So the first question is about the method you use for the IMU. You use the Madvik filter, right? Like, why did you do like a research before choosing the Madvik filter? Like, or why did you use the Madvik filter? I know there are other methods around, yeah. So this Cayman and other ones. Then for the IMU, because I currently also got all that your components, and they are working very fine. I started testing some of them, and they are well documented, and I really like them. Yeah. So for when you're using your IMU, also now I'm still wondering, because is it possible for sensor fusion? Can you fuse camera and maybe in the future, your future work, can you fuse camera, lidar, and transform, like all sensors together? I think there should be a particular IMU that can like fuse all sensors, right? And my last question, in the design of your project, I know it's open source, but why didn't you maybe patent the design? Because call came in. Why don't you patent the design? Because it's very unique.
Okay.
Sorry. Yeah. Did you get my question? So why didn't you patent the PCB, the design? And what software did you use? What software did you use in designing the electronics layouts? Because for some of us have like experience in Arduino, but we don't really know how to like if you want to do a future project from scratch, and I already have some Arduino components, how can I integrate it with ROS? You know, how were you able? Where did you get this knowledge? Where were you? How did you learn how to integrate Arduino and ROS together? Yeah, those are my questions. Yeah, thank you.
Okay. Thank you for the question, Mr. Samuel. So first, as regard the research, like why I use the magic filter and not maybe some other algorithm. Actually, initially, I started with camera filter. Actually, so you know that the truth is that there are open source, there are open source codes out there that you can actually try out. You understand? For some of all these projects. So I think I was able to get one that it's research and it's paper and things like that. So I tried it out and did some tests. I used the Kalman filter, but there's a problem called gimbal lock when using a Kalman filter. And I've been reading about gimbal lock, and I saw the issue. So if you check let me just go back to the video a bit. Sorry. If you notice the video, I don't know if I did the test here. If you notice, I was able to move it upside down, and it's not the each of the transform is not behaving unusually. So it's just very good. So, and I realized that using something like a magic filter, number one, has is good with all this transformation, especially when I'm doing things like row, when I'm doing my row, the magic filter behaves very well. You understand now? So it was based on research. So I shifted to using magic filter. I think with the help of this particular 𝗟𝗟𝗏𝗏 robotics, they have a very good magic filter ROS node. So with the help of, I think with their help, I read some of their works and things like that. So they don't actually help me in this. Their work helped me in the implementation of this magic filter. And because number one, it's easy, it doesn't have the gimbal lock problem. Parameters to set up are not just basically one parameter just for you to tune. You understand now? For common filter, there might be other parameters you might need to tune and things like that. So I think it's just easy. Since I was also something I also release to people, some might not be very used in you are dealing with consumers. It might not be easy. Start setting this one, setting up this one, confusion and things like that. So I think I just stick with the magic filter since I was able to come up with a way to integrate it into embedded code. You understand now? So I stick with the magic filter because of its ease and the fact that it doesn't have gimbal lock issues. So that's why I stick with magic filter, not other camera filter. I've used camera filter. I think I still have the code archived somewhere. Yeah. So as regard the sensor fusion question part. Now, if you like the word sensor fusion, the major thing about sensor fusion is just having your sensors, your different sensors. Number one, outputting the right data. Now I'll be using ROS as an example. Once you have your sensors, whether IMU, LiDAR, odometry, whatever it is, camera, as long as they're outputting the right data, that's what I discovered. You just need to output number one, the right data and in the right format. Then the algorithms, the different algorithms that are there for sensor picture, whether you're using 𝗙𝗃𝗏, you can use this robot localization package. You understand now? You can try with IMU, bring odometry, or any other sensors you can talk about, fuse it together. So what I did was focus on. I noticed that the problem, like I said, here was just getting sensors number one to output the right data, good data, and the right format. Integrating it into softwares, open source software like ROS became easy, and that's why I could actually use the 𝗙𝗃𝗏 with odometry and the IMU, sensor fusion, to get filtered odometry reading, because the hardware is already working out of the box, sending good reading, precise reading, and in the right format. So to answer your question, I've not actually tested with other, maybe bringing in a lot of sensors. For example, the 𝗟𝗏2, actually the 𝗟𝗏2 and the robots, like navigation, AMCL and the like. This thing uses camera, odometry, and a lot of things. There are actually some fusing that are happening together, some filtering process that are happening together. Now, if the data formats and all these things were wrong, or they are outputting wrong values, number one, something like the mobile bot wouldn't have even been possible. So, but the point is, yeah, good hardware are working well, outputting the right data and the right, format. It means you can now implement them on advanced algorithms. You need to perform a lot of maybe sensor fusion, be made possible. So as regards that could be a point of contribution or something to the work. And I would love to see that if you can do that. I would love to see you implementing it with other sensors. I don't know if I answered that question. Thank you. So to the last question, we talk about me patenting. Sorry, I think after that, after the patent question, do you ask any other question? I wrote something here. I don't know if it was.
Yeah, the design. The design.
Okay, the
Of
software
the
used to
electronic.
design. Okay.
Yeah.
So as regard the patenting side, I think this one came out of.
No, sorry to cut you short. You have to be fast. Your time is.
Okay.
So we have to move to other questions.
Okay. Let me just quickly then. The software uses keycard. Yes, to design the circuit keycard, and I think the free route to design it. So, and one reason why I made it open source, because a lot of things I got there was open source. My research came from open source work. They had licenses already for their work, open source licenses. So it's for the community. So I just decided to make it a bit open source. Like, the patent is something I can consider maybe later. Like, since you brought it up now, maybe. But that's just the so something about it. Yeah.
All right. Thank you. So Kenne is asking, how long did it take you to build this robot?
The robot.
Yeah.
Okay. So the story is interwoven, because the whole point, everything started since 2020. After issues I had based on the PhD research I was working on with my lecturer, we had IMU based control issue. We couldn't set up. That time I was even learning ROS. So, but we couldn't use it. We had to just go back to our usual line following robot and things like that. So it was painful. So that's when the whole research started. So it actually started with the EIMU and the EPMC. So once I was able to achieve them to a particular extent, I realized that this thing is possible. I can try building a robot with it to see if this thing can do what I think this thing can do. And once I was able to build the robot, I said, not people make it open source, probably, or use it to the community. People can benefit, and I believe it will help us here in Nigeria, since these are issues that we are facing here in Nigeria. So in summary, I would say if I want to calculate the time it took me to build everything from where I really started, I would say let me just give or take 4 years, something like that. Because everything is together, both the modules and the robots. Yeah. 4 years.
All right, thank you, Samuel. We really appreciate this insightful session. Although I think I have a question, which is on one of the slides, you have NED frame, NW frame, and what other frame? What are the NED, NW, and other stuff?
Okay. So the ENU frame, the NWU frame, and the NED frame. So these are just reference frame with which you can use your IMU. You notice that a lot of us use this, most of us use IMU. We don't know that it works with reference frame. So the ENU frame is east, north, up. East, north, up. Your X is pointing east. I don't know if you can see my hand. If you can see my hand, this is your X axis. Then your Y axis, east, north, then your Z axis, up. So that's just the reference frame. Now the northwest up is your X is pointing north as usual. Your Y is pointing west, and your Z is pointing upward. The NED frame is just like the reverse. So more like X is pointing north, your negative Y, and Z is down. So it's just a reference frame. Now the major take home that I'll just is where you can use them. Your ENU frame and the northwest of frame are generally used for ground robots, robot that works on the ground. So generally mobile robots use these frames. While the NED frame is used for robot that work in the air, like your drones or aviations and things like that. So I think that's the major thing. And the default reference frame for as ROS developers for people that work with IME is the ENU frame. That's their default reference frame. Thank you very much.
All right. Thank you, Mr. Samuel. There's another question here. You can ask the question.
Mr. Samuel, so from the robots so far, I can see that it's a kind of complex design. I just want to ask, what is your workflow like? Because I noticed you use KiCad for the circuit design, where you use ROS to try to simulate another thing. So where do you start from when you want to design from scratch? Thank you.
Okay. Okay, thank you. My workflow, where I start from when I want to design from scratch. As regards some of all this, I think first, usually I usually will write out, draw out my plan, what I want to achieve at the end. That's where I usually start from. Then the next thing is, can try out simulations. I've been building mobile robot simulation for quite a while now. So I try out simulations. I check what this sensor output, how is it outputting its data? Why is it behaving like that? I just check a lot of all these things. So when I'm now working with the hardware, so my major aim is, okay, how can I get an hardware to work this similar manner? So I break them down. I try to break most of the problem down into smaller chunks of problem. For example, I go to the odometry side. I realize that I need to be able to get odometry data from my encoders. How will I get that? I need a way my hardware is to communicate to my laptop. I need to work on the kind of serial communication, or you can use micro ROS, but I didn't use micro ROS. I used a different way of solving the problem. So once I was able to get it to communicate, then okay, where should I run the PID code? Should it be on the robot or on the actual computer? So these are questions like that I keep asking. So it's more like sometimes I work on it. I might try some things. If it didn't work out, I'll go back again, then try it again. So then I go simulation to get what I want, how I expect this thing to work. And I start working on the hardware to see how I can get it to work at least somewhat similar to what I'm expecting. Then I apply softwares as necessary. If I need, most times before I do any PCB design, I always build it like with my hands. Yes, like just do normal soldering and that's what I do. I have a lot of these samples here. So and it might not be a good workflow, but that's what I try. I try those things out before then I do the PCB. Yeah.
All right. Thank you so much. I really appreciate this session. Although I think we have one more question, but we don't have the time to take the question. So if you feel like you still need to ask Samuel something else, I just dropped his LinkedIn profile on the chat section. You can reach out to him on LinkedIn, message him, ask him anything. He's a robot man, so we always we attend to whatever question you have. So I also want to say something because of the technical issues we are having on the physical side of things. Whenever somebody asks a question, I will employ my speaker to please help me re-echo the question. So when you repeat the question, then the people here will actually hear you. I know our online people don't have any issue with that, but we have an issue with something like that. So when anybody asks a question, repeat the question so that people here can hear you, and then you can then answer the question as well. Thank you so much once again, Samuel. We really appreciate the session.
Thank you very much.
So moving on, we have another speaker here, and there is one of the things we are trying to do as a community actually in Nigeria. One of the key things we are trying to do is to make sure that we can actually practice robotics in Nigeria. We know how technical, how difficult robotics is. Robotics is really difficult. It's technical, but we want to make sure that, you know, we don't just keep saying, oh, it's difficult, it's technical. There are people who have actually done some stuff in robotics, and we can actually learn from them. And one of the people actually is what we just heard from Samuel, making amazing things. And another thing we want to talk about is a control problem. When it comes to robotics, in fact, when you're looking for robotics jobs and things like that, some of the things they want to see that you can do is to write a good control algorithm and be able to use it to, you know, solve problems. And some of these control algorithms, you can see they are like mathematical jargon, a lot of things inside, a lot of mathematics. And in fact, even knowing how to implement some of these things is actually a problem. And we don't want people to, you know, have that kind of a problem. And then that's why we're bringing in people who know different, you know, aspects of robotics to help us out on it. So we have Femi Ayoade here. So Femi is a robotics researcher in the US, and he has like good experience in robotics. And he wants to take us on a particular aspect of robotics, which is using the linear quadratic regulator. It's a control algorithm. So two things he's going to do. He will explain the whole LQR, the linear quadratic regulator. And then on the other side, it will actually show us how to implement such a thing. Because one thing in robotics is knowing how to talk. People know how to talk, but can you actually show us how to do the real stuff? That's the thing about robotics. So Femi will show us the slides and everything, and also, you know, he's going to let us know how the thing actually works. So Mr. Femi, the floor is yours. Take over.
Okay, thank you so much. Can everyone hear me? Hello? Am I audible in law? Hello?
Yeah, we can hear you clearly.
Oh, okay. Thank you. Thank you so much. So my name is Femi Ayoade, and as he rightly said, I'm a researcher. I love researching, though I mean, of course, my primary work is just to do, you know, software engineering with a firm here in the US. But I mean, that is just my, you know, the stuff that bring food to my table. But actually, I have passion for robots and for robotics, and I really love to see how maths can be turned to code. You know, how you can use maths to solve real life problem. And that is the reason why I want to talk a little bit about LKR, which is a full state feedback controller. So before I start, I know that most of us we are really familiar with PID, which stands for proportional, integration and differential controller. So, and in PID, you have to like be having just one, you tune maybe the angular velocity of your let's say you tune the angular velocity of your motor, or you tune the linear velocity of your motor. You just have to do everything one after each other. And you can really find that PID controller in most of the hardware interface implementation on Rust or on Rust 2. When you are doing your hardware implementation, you notice that, okay, most of the time they use PID controller, and you'll be seeing that they are using just a single, one after the other. So they have the K, which is like controller gain for the P. They have K for the high, K for the D. So they have it like that for all of them, and they try to tune different part of the states at a time. But for LKR is is a state full. It's a full state feedback. That is, it's just taking everything and just pass it through the box, which is the mathematics box, and it will spill out the desired output for you. So let me not go through some of because we still have to go through a lot of code, and it will take some time to go through that. So the first thing is to develop a full state feedback controller with the optimal gain matrix. And as I've said earlier on, that we try to match up the the gain, which is the key, with our states. And the solution that we are going to use is the techniques of what we call the LKR controller, so which is the linear quadratic regulator. So basically, go to the next slide. We use entire states vector to compute controller inputs. So what are we talking about when we talk about state vector? So state vector is actually like, for most of us, like maybe you have a mechanical background, they talk about developing a governing equation of a system. And if we are to look at the ABC of maybe, or the LO word of dynamics, we talk more of pendulum. So you develop the governing equation of a pendulum. You develop a governing equation of like an inverted cat, and those are the, more example, like simpler example that we can use, and we try to create their state vector. So state vector could be a dynamic, could be derived from a dynamic equation of a system, or it could be derived from a kinematic equation of a system. So we try to differentiate between when we are to use a kinematic equation of a system and a dynamic equation of a system. But basically, for this presentation, we are going to use the kinematic equation of a differential drive system. So we have, of course, we'll be looking at how the gain matrix key influence the system behavior during our during our presentation, like quick video that I'm going to show, and also of course, to achieve the the desired behavior with the minimal effort. So so let me now start with the LKR itself. So as I've said, that LKR is a full state feedback controller, and LKR is one of the control method that we use in optimal control. So for in control classes, we have classical control, classical control, like the PID. So PID is like a classical control system. But for LQR is a optimal control system, and it belongs to other type of control system that we normally see as like modern control system, whereby we talk about different form of stuff like the Lyapunov equation and so on and so forth like that. So it's another like a system of controlling your model. So and the reason why we choose LKR over any form of other controller, over any form of optimal controller using optimal solution like optimal control, is because LQR is I can call it the basic minima way of using optimal control. So let me say it's relatively simple to use because it's just like a building block in our optimal control solution. So if maybe you want to go into your master's program, and you want to because in my master's program at Southern Illinois University, I majored in control and dynamics. So of course, I have my undergraduate in something different, and as a Nigerian, you have to grind, you have to you can't say no to it. So I was new to control system then, both classical and modern control. I was new to them. So, and my prof said, you know what, Femi, you have to take these two classes. So I was just a new student, and the first lecturer was a vibrant lecturer, and he's also from Asia. He was like, okay, he was teaching us I don't even know that all those zignanipoko and all those terms and that like that, and I was new to it. But of course, that is not to scare me. The same thing for the modern control class. So we are taught a little bit of all those form of different equation in classes. So we shouldn't be scared when we see something like this, like, oh, this thing is J equals to integration having lower higher limit of blah blah blah, like that. That's not to scare us. It's just like notation. So and I will go through this also. So so we have the function. So basically, when we are talking about optimal control, so we normally look at it from the perspective of costs. So maybe take, for instance, you want to build a house. Of course, you can build a bungalow, you can build something else. So you have a cost attached to that. And also the basic of this thing is the cost. So we have the cost for everything. So in this situation, this J represents the cost, and we are looking at this. So anytime you have this kind of integration, so you are looking at it from the perspective of a continuous system. So when you have integration, you are looking at it from a perspective of a continuous system. And when you have like the summation, like the summation equation, so you are looking at that from a discretized perspective. So basically, this is just like a math jargon for like continuous system that we are looking at. So, and here we have X, we have Q, we have X, and we have U, which is a transpose, and we have R and we have U. So basically, I will quickly just pinpoint on this Q and R. So Q is just to penalize the state. So this Q is a matrix, and this R also it is also a matrix. So, and it depends on your system. So S is just the state of the system, which we are going to discuss about. U is just the the inputs to the system. So, and we will discuss about that also. So those are just some of these things that I want us to take care of when we are looking at it. So anytime you see anything simple function, especially when it comes to control system, you have to have something like this at first. And So now we are looking at two things. So for a system, when we have a system, we have our robots. Take for instance, from what Mr. Sam said, we have the normal AMR or grand robots, and we tend to, like in simulation, of course, you can try to create, like, take for instance in Gizebo, there is a way you put in kind of natural environment in place, like making a kind of normal situation of our environment. So when we have our robots, we tend to, in our brain, we tend to have like, oh, we have a kind of a deterministic environment. Deterministic environment say that, oh, there is no noise, no disturbance, nothing, everything just, smooth. But in actual sense of it, nothing is smooth. We have a lot of noises. I mean, even within the robot itself, and we also have a lot of noises, outside the robot itself. So we have the kind of exogenic stick disturbances. Those disturbances are very, very, they are very, you can't even predict them, just like wind. You might be going and wind can just blow your car or something like that. So with this type of controllers, take for instance, you are moving, your robot is moving and it's just wind is blowing. So there must be a kind of resistive force from the control from the robots, and for the robot to react, then it's actually need a kind of a controller to do that. And so because we are not having this deterministic environment, we have a kind of stochastic environment, so to say. But because of LQR, we try to downplay, we try to make it seems like, oh, we are having a a a a deterministic environment. So now that is like a layman part of it. So now what I mean now in the mathematical sense of it is that we call LQR linear quadratic regulator. Normally our system is non-linear, but because of LQR will try to linearize the system. So, and for us to linearize our system, take for instance, we might have like different variables before, but because you try to linearize the system, you try to make the system to have a kind of like simpler variables, and you make it a linear system. And we can employ different mathematical techniques to linearize your system. So by linearizing your system, you are making it a kind of a deterministic system. And all those mathematical method are like Jacobian, Taylor series, and so on. So those are the, you've learned a lot of Taylor series in your undergrad. All those things, you can apply it in the real sense of it, to control your robot. I remember then when I was doing my one of our projects on drone dynamics. So we have to linearize the system of, like, we have 12 different equations, 6 for rotation and 6 for translation. So you have to like linearize your system using Jacobian, and also even using some Taylor series of stuff like that. So it was a lot, but of course it was fun stuff. So now and that is it. So, but as for stochastic environment, so the stochastic environment is, sometimes when you have like double pendulum and you are moving it around, it could have a kind of behavior, a kind of chaotic behavior in an environment, and before you know it, you won't be able to control it. But by the help of stochastic, there are some stochastic algorithms like that can help to minimize, to downplay that problem. And for you to even go into that stochastic algorithm, you still have to have a good knowledge of LQR, because LQR is a building block. So you have to build on it to use other method like Poitras method. So, and which of course it is out of scope of this slide. So The next thing now is our the Hamiltonian and calculus of calculus of variation. So basically, we have the control Hamiltonian. So that this basically what we want to get the equation that we are going to formulate into our that we are going to bring into our code. But this is like a step to it. So from here we have the H itself. I mean the Hamiltonian itself is being derived from our calculus of variation. So and so this L, it's just the running costs, and this lambda transpose and FSU is just the system dynamics. So and we are going to do some derivation whereby we get our states, co-states, and some other needed equation to form our to form the solution to our problem. So we have the system dynamic itself. So basically we have x dots equals to ax plus bu. So this is the simplest way to represent our system. So but I will love to explain this in the next slide so we can see how to go about it. So but basically x dots here, it implies that we are dealing with a kind of a continuous system. So and when we have x dots, when you are going to bring this kind of stuff into computation, then you have to discretize it, because our computational power is through discretization. So you have to discretize your system for you to have this work in your in the coding environment, like creating a computer stuff for it. So we formulate the quadratic cost function. We develop the Hamiltonian, and we apply, just as it sees in the slide. So basically, after writing out everything, the main thing is that we want to, give, maybe take for instance the differential drive robot that we are going to use. We want to give it a right input. So we want to give it a right angular velocity. We want to give it the right linear velocity. So, and that is why we have u equals to minus k of the system. So k is the gain and x is the state of the system. So the first thing here is now the cost. So basically, if you can go back to like this slide. So basically we have, this is just this equation that you are having here is basically the same thing with what we have here. But however, we had something to it. So, and we had our terminal cost to it. So, and this is the normal cost, which is the running cost. So basically we have J, which is the cost function, as the terminal cost, and the it has the running cost. So, and if you check from this side of it, we have H equals to LSU, L, which depends on X and U, and this formula also. So we have the running cost. So this one, we capture the running cost, which is the Lagrangian, or the running cost, and this we capture the dynamic of the system. So when we go back to it, so this is the terminal cost, which we are also going to use, but this from here to here is our running cost. And so when we now go back to the equation that we have before, we said L L, which depend on S and U, and lambda transpose with X, and our X is the state of the system. So that is how we have it here. So we just pick this one out, right, and we put it here. And as I've said earlier on, don't be like tricked with this integral this thing. So of course we are still going to use it, but we integrate it from 0 to final time. So but we are going to, since we are using summation, so we are going to add it over time, so we don't have to bother ourselves with this. So don't like, but you guys, you just remove this and you bring it out. No, since we are using it on a system, we are using a discrete time, so we have to discretize it. So we have this 1/2, this like this, and also this, and we also have a Hamiltonian function. So we have it in this, and the next slide. So we now have, so under so we discussed that we are going to get our solution through the use of calculus of variation, and for us to achieve that, we have some different stuff to do, which is to fulfill, like conditions to fulfill, and that is our states, optima, and different conditions under the calculus of variation. So basically, we are the first one to do here is to minimize the costs. So that is our point of what's it called? That is our goal, is to get a minimum results for our, optimal result for our inputs to the system, because we want to give the right input to our system, so that should behave well. So we have the first thing here, which says the partial differentiation of the Hamiltonian we differentiate it by the state. We have this output, which says it is state. So basically, we said the partial differentiation of Hamiltonian with the partial differentiation of state should give us this. That is the that is what the equation says. And also for the co-state equation, that one also have its own also, that okay, the partial differentiation of dh d lambda should also give us s dots. So, and that is how we have those one also. And for the other one, which is the optimal control condition, is that one said partial differentiation of the Hamiltonian with by partial differentiation of u, which is our input, should give us 0. So now we now go back to this. So partial differentiation of our h against different dependency like the us and lambda, which is of course our Lagrange multiplier. So based on that, we derive all these equations. So when you do dh dx, then you derive the equation. So before I go, remember that the x that you are having here, qt, xt that you are having, these are all they are all in matrix form. So when you are differentiating them, there is a way to differentiate them. There is a law that guides how you differentiate a matrix other than just normal differentiation. So when you have, so most of the time when I want to like remember something, I will try to use like, okay, when I have something of this pattern, it implies that I'm basically having x squared. So when you have x transpose q s, so it just basically implies that you are having x squared q. So when you want to differentiate, maybe you want to differentiate dh dx, then you are basically differentiating x squared like that, which will be equals to x, xq, and that's 2 square we cancel out half. So, and that is how I normally like think about it. And of course, that is true, but you just have to go through the step of how to differentiate in matrix, not just normal this thing, because all these s that you are seeing here, they are not just single value, they are in matrix shape. They have a lot of variables in them. But because of our time, it will not really permit me to go through a lot of these things. So we also have the last thing, which is the transversality of our states. So this transversality, it's helps to we have that is why we have the terminal cost here. So this transversality helps to now derive some information from our terminal cost. So the transversality conditions state that when we have the phi, which is our the phi here is talking about the terminal listing by ds. So this is normal, of course. This is that is the formula for that. So we have the phi, which is the terminal cost by ds, give us qtx, just as I've said earlier on when you are differentiating matrices. So you see S transpose Q S as just as S square, because that is how it is. Of course, you just have to, that's why you have to just do some just to do some brain this thing. Like when you do some brain test, you will notice that, oh, so this is how the pattern will just figure out for you, and you notice that, okay, so when we have like x q s transpose, basically you are essentially saying, oh, we're having x squared. So yeah, so and I think I will send a link to one of the Medium posts that I have for this, showing steps you can take in deriving all these things. So, but essentially, in mathematics, we have some assumption, and basically, the two things I want us to notice here is that, of course, we have our cost function, because anything optimal control must have cost function. So we have our cost function, and we want to get a optimal solution to our problem. And the problem here is that we want to, like in this case, we are talking about a differential drive robot. And mainly for differential drive robot to move, it needs a accurate velocity. So it needs a velocity in linear x direction, and it needs a velocity in angular z direction. So because the angular z and the linear x, that's the main velocity. The other lateral one, which is y, we don't really want it a lot, because that can even cause spinning and so on and so forth. So basically, main thing that we need is the angular z that will make it to snow when you are steering the vehicle, and also the x direction. That is what we need, and that is our input to the system. And we need the optimal, that is, we need the optimal value for this thing to move. So therefore, we have our u that we are looking at. So now that we know that this is the formula to get the u, which is u optimal, and now we know the terminal cost, which says qt, q of the time t, and s also of the time t. Sorry that this latex is, but it's just like time t. Sure. So s at the final time t. So we know this, and we now have to assume, based of the knowledge of our final time. So we know that at final time, our lambda, which is our Lagrange multiplier, will be equals to qs of the final time. I mean at the final time. And since we know that, then we will now try to do a kind of extrapolation. We will now try to extrapolate it to all other times. So at every point in time t, we say, we now assume, because that is where the assumption comes in, that lambda of that time t should be equals to q of that time t and s of that time t. So from there, we now begin to substitute in this value of lambda into all our equation. And from there, when you do the solution, you come into what we call your the Riccati differential equation. I mean, when you just do the algebra, you know, just calculate, substitute, and you will get it. But I have that Medium post. I think one of our admin will help us to share it with us in case you want to look into that, how I derive all this formula. And of course, you can even get it from other places, but you can just check out that post. It's really explaining it on how to go about it. So the next thing is the formulation of our discrete time state update. You know that before now I was talking about this, that our S here is just a linear system at this point in time. So we have X dot, X double dots, and so on and so forth. But in this case, we want to discretize it. We want to make it per time. We are not sorry, sorry. Sometimes I do mix linear and continuous. Sorry, X dot is a continuous system in this format, but we want to discretize it because we want to bring it into our computer, because computer work by time, like 0.00 something seconds. So we don't use continuous system in this situation. So now we convert it to a discrete system. So we have at time k plus 1, and so on and so forth, like that. So from the differential, from our differential drive system that we want to use, I don't have the link here, but there is a link to how to get the dynamic equation of a differential drive system. And I told you before that I will talk a little bit of the dynamic equation and also of the kinematic equation. So basically, this one is a kinematic equation because all we want to achieve is the kinematic problem, such as the velocity problem. That is what we want to address. But when you want to address your force, when you want to address your mass, and so on and so forth, then you are going to use your dynamic equation. So when you are talking about governing equation of a system, you can talk about the dynamic equation and you can talk about the kinematic equation. And sometimes they can use them interwovenly to say, oh, what is the equation of motion of the system? No, they are all these things, they have their own time that you have to use them. So, but in this regard, we are using what's called the kinematic equation because we are focusing on just to move our robots. We are not considering the the mass of the body or something like that. So since we are using that, so this is how we have arrived at this. Like you can look that one up, and we arrive at this equation. So we have our A matrix, which is this. We have our S. So in this regard, S will be 3 variables. It will be one for the what's it called in x direction, in y direction, and in angular z direction. That's the state, the position, that is the position of our robots in x direction, y direction, linear x direction, linear y direction, and angular z. Yeah, so it will be normally, that is why I have x, y, and theta here. And also for our u will be velocity. Now want to move it, right? So we have our velocity, which is essentially in x direction, and our omega, which is essentially in z direction, that is angular z. So that is how this one is, and we are going to see it also in code. So we have of course, the implementation of this within the ROS framework. So of course, we actually know that our previous presenter made mention of the NAV2 control, because in NAV2 we have the section for the controller. So we have the section for the for different times of when we talk about controller, and we talk about planner. So we have a global plat planner and we have a local plat planner. So the local plat planner is one of them is this 𝗟𝗂𝗏 that you are seeing, and some other one are model predictive controller, and that one is a little bit, of course, more higher than 𝗟𝗂𝗏. That's why I said 𝗟𝗂𝗏 is a good thing to know about 𝗟𝗂𝗏, because it's the the building block. So all those controller, they have it inside the nav2 stack. So when you are running your nav2 this thing, you are going to see those controller embedded in it, and that is why we have that 𝗟𝗶𝗴 controller. So they have it embedded in it, and that is for the local part planning. So, and of course, when you are dealing with all these things, you will be hearing it a lot in control, in all these things, that you have a local, this thing, we have a global, so something, global minima, local minima, global optima, local optima, and so on and so forth. So we have this, the component that we're going to use, of course, the node for ROS2 node for estimation of state and so on. And we also have the publisher and subscriber. I mean, that is the main part of this thing that we are discussing today. So basically, the first thing that I want us to know, I mean, these are the main part, aside from the boilerplate, these are the main parts of the code. So the first thing, when you have, I believe we are all familiar with ROS2 node here. So when we have our system, Mr. Sam talked about IMU sensor, and we have other form of sensor also, like different forms of sensors. So basically, you have your hardware, maybe you have your IMU hardware. So IMU hardware, if it has no driver for ROS in it, it will have some kind of sending stuff, like it could send some messages from it. Okay, all those coordinate that is having, it will have a kind of message that is it will have, they call it packet. So it will have a packet of its own that have the ID, frame ID, and so on, and the data in it. So those packets, it will now send it over to what's it called, to ROS2, and ROS2 will have it wrapped in its own distance. So basically, the message for IMU will be under this format. So these are very essential parts of this. So when you are running this, you say ROS2 topic echo, ROS2 topic list. All those things, they are very essential in what's it called. So when we have it here, just take for instance, we have ROS2 topic list. So before you start writing something, these are okay, since I'm not running anything, if I to like take for instance, if I'm running like old, okay, because of that time, but I can still run it later. But when you have the ROS2 topic list, it will show you some of this information which are very vital. So when you have this one, then this is the message type, and you are getting it from your from the sensor that you have. So the sensor give you the velocity of the of your robot, like, okay, this is what your velocity is. And this ODOM topic also will give more information on your position of the robot in the environment. And from there, you are getting the information that you really need in controlling your robot. So, and here, so basically, this one is the command veil. So you can say that this is a publisher node. This one is the subscriber node. So subscriber in this form is doing what? Is getting information from your sensor that you have, whereby the publisher node is sending out information to your robots in this case. So the publisher node is sending out the twist message type to your robot. And I have this timer here. So this timer is just basically executing these tasks every 100 milliseconds. So for every 100 milliseconds, this task, this function will be triggered. So when this function is being triggered, then of course the twist velocity that you have here, you will be, it will be sent to the robot. So that's essentially, so this place is just to get all the essential information from our sensor. So that, and this is the connection, this is like a pipeline for it that you have to have at the back of your mind. So now, after getting all those stuff, of course, there are still part of the code that I might have to show now just for you to get. But because of our time, these are like more essential because I have to show the formulation also. So now we have the function that we name do_LQR. So it's basically that is the function. So and to get some of our needed information, we have the current states of the robots, that is the current position of the robots, and we also have the destination that the robot is going to. And we now have, of course, the reference input. So normally we want to give this robot, let's say the robots, we are sending like some velocity to the robot. Like, okay, this is the amount of velocity that you need for you to move through this part. And before the robot gets this information, we have to pass it through this block. And this LQR will now help us to give us the exact, what's it called, exact points, the exact track that we need to give the robots. And one thing about movements of robots, when you talk about robot path planning, it's good thing to tell you that, okay, because this thing is a discrete system. So just imagine having a signal that have been sent within like maybe 50 hertz. Just convert 50 hertz to seconds. You know that is very small millisecond. So within a second, you've already sent like 500 or 50 data just within a seconds, or maybe 100 data within the seconds. So and that is how robots do work. So robots use points. So you might have a distance from A to B. You calculate an Euclidean distance from A to B. Robots will draw a point just as if you have your graph, just the graph that you normally have in your class. Like, so robots will just draw that point. So as your robot is moving, it's moving through that point. Okay, from point A, it moved to point B, it moved to point C, and so on and so forth, like that. So that's how your robot will move for that thing, for that motion to be for that movement to be achieved. So it have to move from point A to point B to point C. So now, and we know that, of course, at a time, your robot base will be at a certain point. And that's why we have this current state. We have the desired state. So the desired state will now be the next point that you want your robot to be. And we have now the reference input. So the reference input is just like, okay, just like a previous input that you give to the robots. But now you are now passing it in as an argument, because you are going to use it inside your equation. Like you can see here, so U is our reference this thing for our previous time. So this one is just like previous time. This K that you are seeing here is a previous time, and K plus 1 is the future time that you are going into. So, and that's why we have that reference input. So we have the reference input here for that. So we have of course, our A matrix, because that is the model of our system. So, and the model of our system, we have our theta. So this one can be just give it, the current, from the current, what's it called, current position. You will definitely get your theta value. You definitely get your theta value from the current position. So, and that is
hello.
Okay.
Sorry to cut you short. Will you have 10 more minutes, please?
Okay. Yeah. Oh, sorry.
All right, you can continue.
Okay.
You can.
Yeah. Yeah. So sorry that. Yeah. So nice. So we have the A matrix, and you can see from here. So we have the reference inputs at 0, reference inputs at 0. So basically, in what's it called, in C++, we have vector, we have list, we have array, and so on and so forth. So I love to use vector a lot, because I just love that thing. So, and this vector is it takes in data type double. So, and the reference here is just size of 2. So it have 0 and 1. So at index 0, we have the velocity. So at index 0, because reference u, this is reference u. So it have index 0 and index 1. So index 0 is v, index 1 is w. So we have the reference inputs. Of course, from the equation, you see that is minus v times, so reference input times STD sign, sign, and this one, desired state, right, which is the position of what we want. We have the 2 here, and that's the theta. So we have the theta here for what we wanted to like use. And the same thing, we have the t. So the time t is the rate at which the thing is coming. So, and that rate, you can get it from your clock timer. So, and that one will just give you, or better still, if you have it in mind that, okay, I want this thing to be passed maybe in so amount of time. So you just do the frequency and you get that rate. So that's the dt here that we are having. So we have the reference input also for the second one. And you can see here that I'm using Ēģeņ matrix. So we have the Ēģeņ Ēģeņ here, which is, I made it an identity matrix for now, because identity matrix, you just have 1, 1, 1 in the middle. And if you look at this pattern, you will notice that it's a form of identity before we merge in these two stuff into it. So I have them, then I just modify those two stuff, like 0, like line 0 and index, and the like index third, like the first line and the third index, which is the last index. So, and this one also the second line and the last index, and that is how I fixed in this thing. And the last one for that one, of course, supposed to be dt, which I didn't include in this thing there. So we have that of B matrix also. So we have the, of course, sine theta. The same thing applies to these, based on the equation that I gave at the top. So yeah, so the next one now is now the formulation of the matrix itself for the for our discrete algebraic Riccati equation. So we have so we now have numbers of iteration. So, and I have to like discuss, time will not permit me, but basically we have the P matrix, the Q matrix, the R, and normally, so a little bit of what's it called here, when we have, so in this place, we have our S. So the shape of S will be, we determine the shape of Q. So take for instance, maybe your S is something, maybe your X shape is M by M, or maybe your X shape is M by N matrix or A by B matrix. So your Q matrix will be B by B matrix. So that is how you do the matrix formulation. So and that will definitely match. So when you are doing that, you must have that at the back of your mind. So, and we know here that if you have this, so we have so we have the Q matrix here. So I make it the identity of 3 by 3 because based on the shape of my X matrix. The same thing with R based on the shape of my U matrix. My U matrix is 1 by 2. So definitely is R matrix supposed to be 2 by 2. So I'm coming, sorry. Okay, so yeah, so I'm so sorry. So I have to round off soon. So you can go through this code later. I think they will share us the code. And in case you have question, please let me know. So basically this one is just like doing normal transpose. You can see the name implies a lot of, give us some of this thing. So so the same thing also go for this, and this is a PNOM is a good way to, of course, but my time is up from what I'm getting, so I have to like, but in case you have any question on this, please let me know. So let me quickly go to a quick demonstration. I think I can even play the video because there's no time to. Yeah, so I have the video is a little bit this thing here, but so
So you are running the code, right?
yeah, I'm running the code, and yeah, so no, I mean I'm playing the video, and the video is a little bit this thing. I can even run the code. I mean, I can just run the code, but since I'm playing the video, I think I can just use that for now. But basically, the robot will move just in an L shape. So yeah. Oh, shoot. Yeah. So I mean, the video that I have here is a little bit wacky, so it's not really. It's just moving slowly, and yeah. I mean, the frame per seconds movement of the video is a little bit sluggish, but yeah. But yeah, I think I should be able to.
All right. So while you guys are watching that, again, it's good to know that this this meetup will be available online. So when we are done, we'll post it on YouTube and then share the link with every participant. So it's going to be available online. The slides as well will be available online. We'll give you link to the slides as well as the code. So the whole code, everything about the 𝗏𝗏𝗿, the LQR, everything will be available online, and then everybody will have access to the code. But right now, if you have a question, you can. I can see a lot of stuff here. Okay, so somebody's asking if it will be shared. Yeah, it will be shared.
Okay. Yeah.
Okay. Mr. Femi, somebody's asking that
Yeah. Okay.
C++20 now has STD span. This can take in both fixed and okay, this is just like a suggestion. All right.
Oh, okay. Okay. Yeah.
All right. Thanks for that. And the person asking this question, I think I need to talk more with you. I like that you're mentioning new features in C++. So by the way, if you have a question, please kindly take up the mic and then ask your question. Anybody have a question? Okay, we have someone here. Okay. So again, please, anybody that asks question, our speaker kindly repeats the question for other people to hear it.
Okay. Okay. Okay.
Thank you for the presentation, sir.
Thank you so much, brother.
So I want to start with control systems.
Okay.
I'm actually into control system,
Okay.
attitude control systems.
Okay.
So I have 3 questions. Let me make it quick. The first question is, what is the workflow like? Because we know in control system, it has to do with a lot of mathematical modeling where you want to twin the parameters to ensure that the robot performs the right motion and efficiently. So in terms of the workflow, what types of mathematical modeling method did you use to do the modeling of the equations? Like, let's say, using of quantiums, do you use Euler's angles? what kind of in terms of using Hamiltonian Elangaji, how does it go? So that's the first
Okay.
question. The second question is
Let him answer the first question.
okay.
Okay. Okay. So yeah. So the workflow is that
Can you help us repeat the question if you can pick anything from it
oh
so that people
okay. Oh, okay. So you are asking about the workflow of like creating the model of your system down to controlling it, right? If I'm getting it.
Yes.
Yeah. So and how does the Hamiltonian, Lagrangian, and so on come into play,
Yes.
right?
Yes.
So yeah. So basically, for you to have a system, you definitely have like, okay, you have the normal equation of it. Like take for instance, you are using normal Newton way of doing things, like using like
Yeah.
you want to generate your equation of your system. Like I'm looking at ODE, like ordinary differential equation. So you are generating using like like Lagrangian equation of like L equals to T plus U, whereby you differentiate them and you have that equation. So when you have that equation, like
you can show the slides while talking so that people can.
oh, okay, I don't even have the slide for okay, I don't even have the slide for how to create a equation of a system, but I can share some links for people to look at it. So basically, you can use normal equation of normal F equals to MA to do your to start your equation. But most of the time, when we are dealing with rigid body, we normally use what's it called? We normally use Lagrange to generate the equation, and that equation is not here though, but you can use Lagrange to generate more of your dynamic equation. So when you generate that, then you will now try to formulate it to match this pattern coming up to match this pattern, which is x equals to ax plus bu. So this implies that in this, let's assume that okay, you have position, you have the velocity part of your equation. So you make sure that okay, you are matching the velocity parts of your equation to be in this place, like in left hand side, and you put your what's it called position in right hand side of your equation. And also you have the input, maybe there are some inputs in that system that you have, like maybe in form of this thing, then you put it in this side. So basically your main equation should be x dot equals to ax, because and a will now be the like I don't know how to put it, but like a constant or a variable beside your s. So you just choose I mean I can show like a math this thing, maybe just to go through a simple this thing after the meeting. Maybe I can hook up on that, on how to create a formulation of this kind of equation. So, and after that, when you have this already, then you will now proceed. So you have your governing equation. From governing equation, you form the state space matrix. So that's this thing is called state space matrix. So you form the state space equation, and when you have the state space equation, you move down to now bringing in that state space equation into this cost function. So no matter what, you have your state space, and inside the state space, you will definitely find all this stuff in it. S, because your S is definitely the state of your system, and the U is the required input. So you find that and you bring it in. And that's why I was saying that those ones, they are just like matrices. So they are not just a single value, they are matrices. So, and that is how you bring it into this. So yeah. So, and from there, you take it down to code.
All right. Thank you. I think he has more question, right? Yeah, go ahead.
Yeah.
So, thank you, sir. So I think we'll continue conversation on that. The next question is, do you have any resources to recommend for someone who wants to go into control systems and doing this kind of modeling?
Yeah, definitely. So I will say this, that
Can you repeat the question, please?
Oh, okay. That's let me just I will try to rephrase the question, not the exact question though. That's
Okay.
what should be my advice for somebody that want to delve into control system, right?
Yes, where to start?
Yeah.
The kind of
Okay, and exactly. So the roadmap for someone that want to start with control a dynamic system. So I would say that you should work more on the first thing, like just to take a baby step. Uh, you should work more on your dynamic, on how to like work on all this, utilizing Lagrange equation to get your equation of motion and so on and so forth. And after that, you have to brand more on your calculus, especially calculus 2, because that really help you a lot. And linear algebra, you have to be grinding on linear algebra, because there are a lot of times when we are dealing with sometimes that we normally use, like all these short metrics and so on and so forth. You have to be able to know whether a system is a positive definite, semi-definite, all those terms, all these things, they are inside linear algebra. So I would say your linear algebra must be solid after having good knowledge of dynamics. Then with that, you have to learn more of coding, how to put this thing in code, because that's the the end goal of it, so people can see what you can actualize with the math knowledge that you have. Yeah.
All right, sir. So that brings me to the last question. You have already started thinking on it already. The thing of turning your math model into code, how does it go?
Yeah. So yeah. So based on it.
Sorry, I think our speaker is having poor network. That's why.
Oh, okay. Okay. Yeah. So I think it's better now. Oh, okay. Is Abubakar?
Mr. Femi, I think you are having poor network or something.
Muted before. Yeah. Can you hear me now?
Yes.
Okay. Yeah. So yeah. So I mean, with this example, because I made mention of it because of the time that's in Nav2 stack, we have this code in it, because you won't actually understand the usefulness of having all these turning math to code until you are faced with a lot of problem that it look as if it's not just that it's not it won't be fun at all when you don't have all these things in place, especially when it comes to controller. Controller before now, they really use it in the space of aerodynamics, all those, in terms of people that are working in Boeing and so on. You use it a lot in controlling, in stabilizing the, the plane within the media. And just imagine if you don't have a good control, just imagine what will happen. And the video that I showed, because the time is not really there to show us, I can show you, okay, when we don't have a controller and we have a serious undeterministic environment, and your robot is then, okay, send your robot to a goal. If you don't have a good controller to balance the robots, you won't even get, like, I'm talking about accuracy. I mean, the production, I mean, the response of your robot will not be there at all. It will not just be coming together. But because of this controller, we're able to, like, put the robot together and let them, behave as expected. So that is how that is what I can say about that for now. Yeah.
All right, thank you so much. I don't know if anybody still have question from the online audience. If you still have questions.
I think I saw one question here. That's the person made mention of why is most subscriber and publisher node in ROS created using C++ and not Python. Most of the time, to some extent, I believe the reason why people try to do that is, first of all, most of the in-depth part of ROS framework are in C++. However, Python also, like this code, I can use Python for this code. That is, in fact, is the simplest thing to do. And we even have the library, the eigen library that I used. We have it in Python also. So I can write it in Python, just change all those subscriber nodes to Python, and that will work fine. So there's no big deal in this. But when it comes to, like, writing plugins, the way what's called the framework of Gazebo, is more on, like, C++. So, but the fact is that there is a way around it. If you said, okay, you are just a Python person, I have seen a code before that the person have to use a server, because when you are dealing with, like, MPC, you still need a server to do some stuff like that. So the guy have to, like, create a Python node and create a service. So anytime you wanted to use the Python node, you just call the service, and the service will just make, respond to that node. So ROS made it a kind of, like, this is a kind of interoperable system, such that, okay, you don't really have the knowledge of C++, but you are really, really grounded in Python. You can use that method to communicate. So basically, if you are a Python guy, then definitely I choose, you can just use that route to execute your tasks. But yeah, just for the ease part of it. That is why people, yeah.
Yeah. So thank you so much. I think we're getting to the end of the whole meetup thing. Thank you for our speaker Samuel, and then thank you to Femi as well. Again, as I said before, all these materials will be available online, both the meeting itself and then the slides and the code. Everything will be available online. It's either you most likely get an email from us, and that will point you to where you can get all those things. It's like somebody's raising hand. Sheriff, I'm sorry, our time is up. We won't be able to take that. But then again, feel free to reach out to the speakers on LinkedIn. Samuel is on LinkedIn, Femi is on LinkedIn. And if you feel like you want to ask the question on our Slack channel, we have a Slack workspace. So you can reach out to any of the admins, and then we will add you to our Slack workspace. Okay. So that will be that for now. I really appreciate everybody. I don't know. You want to show your face? You can show your face. Let me just take a screenshot so that we have a picture of everybody on the meeting. So yeah, nice, Sheriff. It seems like you're a basketballer. All right, 𝗟𝗲𝗿𝗂𝗱𝗿, that's my guy. Oh, Samuel Obagwa, thank you. Abubakar. Okay, all right, let me just take a screenshot now. And yeah, it's nice to see you guys. We will meet again on our next meetup. Again, if you are not on our Slack channel, please kindly join. So the meetup will continue physically. I'm sorry, virtual guys. We have to say bye-bye. Thank you, everybody, and bye.